Picture this. You are adrift in the blackness of space. Below you, the Earth hangs like a fragile blue marble swirling with clouds of white. But look up, look out. You see stars, not as mere pinpricks of light but as blazing suns, each one a potential center of its own planetary system. And those are just our neighbors. Beyond them lie billions more, gathered into the majestic spiral of our Milky Way galaxy. And our galaxy? It's just one of hundreds of billions, maybe even trillions, scattered across the observable universe like grains of sand on an infinite shore. This is the cosmos. For most of human history, we believed we were the center of it all. The stars were thought to be fixed points in a celestial sphere, a comforting canopy above our heads. But science has pulled back the curtain on that cozy illusion. We've discovered that this cosmic ocean is not static. The universe is expanding. Every galaxy is rushing away from every other galaxy. But the story doesn't end there. In fact, the most recent chapter has revealed a profound and unsettling mystery. There is a force at work in the universe, a mysterious, invisible energy that is pushing everything apart. It's not gravity, this is something else entirely. We call it dark energy. We don't know what it is. We don't know where it comes from. But it holds the ultimate fate of our universe in its grip. To understand this cosmic mystery, we must first understand the scientists who study it. They are called cosmologists. Think of them as cosmic detectives. Their crime scene is the entire universe. Clues are written in starlight. Clues are written in cosmic radiation. Clues are written in the grand tapestry of galaxies. Instead, their lab is the sky itself. Their instruments are powerful telescopes. Telescopes act as time machines, allowing us to peer deep into the past and witness the universe as it was billions of years ago. What do these cosmic detectives look for? They measure positions of celestial objects. They measure movements of celestial objects. They measure properties of celestial objects. Cosmology is a science built on the shoulders of giants. It stands on Albert Einstein's theory of general relativity. Space and time are not a fixed backdrop. They are a dynamic, flexible fabric called space-time. Gravity, Einstein showed, is not a force pulling objects together. It is the result of mass and energy warping this fabric. Imagine a loaf of raisin bread dough rising in an oven. As the dough expands, every raisin moves away from every other raisin. From the perspective of any single raisin, it looks like it's at the center of the expansion. This is a simple but powerful analogy for what we see in the universe. Rather, space itself is expanding, carrying the galaxies along with it for the ride. This incredible discovery was made in the 1920s by astronomers like Edwin Hubble, for whom the famous space telescope is named. Using the powerful Hooker telescope at Mount Wilson Observatory, Hubble observed that the light from distant galaxies was stretched to longer, redder wavelengths. This phenomenon, known as redshift, is similar to how the pitch of a siren drops as it moves away from you. Hubble had found the first concrete evidence that our universe was not static, it was dynamic and growing. Hubble's discovery was the observational proof of a concept that had been predicted by Einstein's equations of general relativity. He found this idea so unsettling that he added a fudge factor, a cosmological constant, to his equations. After Hubble's discovery, Einstein famously called this constant his biggest blunder. Little did he know, he might have been right for the wrong reasons. The discovery of the expanding universe was a revolution. It implied a beginning. This is the essence of the Big Bang Theory. It's not an explosion in space, but an explosion of space. The universe began as a hot, dense point and has been expanding and cooling ever since, giving rise to the structures, the galaxies, the stars, and eventually, us. For decades after Hubble's discovery, the central question in cosmology was about the universe's ultimate fate. The expansion was happening, but it was a battle against an obvious opponent, gravity, every star, every galaxy, every wisp of gas. This cosmic tug-of-war should be slowing the expansion down. To answer that, astronomers had to measure the expansion not just now, but deep in the past. They needed a standard candle, an object with known brightness. The standard candle chosen was a specific exploding star called a Type Ia supernova. These cosmic fireworks can outshine a whole galaxy briefly and they explode with almost identical peak luminosity. In the late 1990s, two independent teams of astronomers set out to measure cosmic deceleration, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees. They raced to find the answer. They pointed telescopes at distant galaxies, hunting fleeting explosions, but they found the opposite. The distant supernovae were dimmer than expected. They were farther away than their redshift suggested. The only conclusion, expansion wasn't slowing, It was speeding up. The universe was accelerating. The discovery stunned the scientific community and flipped cosmology on its head. The discovery of cosmic acceleration was like stepping on the gas pedal when you thought you were hitting the brakes. It made no sense. Gravity pulls, it doesn't push. What could possibly be powerful enough to overcome the collective gravitational pull of all the matter in the entire universe and push it apart faster and faster? Scientists gave this mysterious influence a name that honestly reflects our profound ignorance: dark energy. Dark because it doesn't interact with light or electromagnetic radiation. We can't see it or touch it. Energy because it acts like anti-gravity, a repulsive force embedded in the fabric of space. So what could dark energy be? The leading candidate goes back to Einstein's biggest blunder: the cosmological constant. According to quantum physics, a vacuum is not truly empty. It's a roiling sea of virtual particles popping in and out of existence for fleeting moments. This activity could give space an intrinsic, built-in energy. If this vacuum energy exists, it would not get diluted as the universe expands. As more space is created, more of this energy appears with it, creating a constant repulsive force everywhere. When astronomers tally up everything, the results are humbling. Ordinary matter, you, me, planets, the stars we see, less than 5%. About 27% is dark matter, and the rest, 68%, is dark energy. We live in a cosmos dominated by two invisible entities we do not understand at all. To grasp the role of dark energy, let's return to our cosmic tug-of-war. On one side of the rope, you have gravity. Gravity is the master builder of the universe. It's the force that pulled together the first atoms to form stars and galaxies. In the early universe, the cosmos was much smaller and denser. All the matter was packed tightly together, so gravity had the upper hand. The universe was expanding from the initial push of the Big Bang, but gravity was constantly applying the brakes, slowing the expansion down. For the first 9 billion years of cosmic history, gravity was winning the tug-of-war. But as the universe continued to expand, a tipping point was reached. The matter, the source of gravity's strength, became more and more spread out. Dark energy, however, behaves differently. Because it's a property of space itself, its density remains constant. About 5 billion years ago, the repulsive push of dark energy became stronger than the attractive pull of gravity on the largest scales. The cosmic tug-of-war was won by the ghost in the machine. From that moment on, the expansion of the universe began to accelerate. This is the universe we find ourselves in today, a universe where on local scales like within our solar system, our galaxy, gravity still reigns supreme, but on the grandest scales between distant galaxy clusters, dark energy is pushing everything apart at an ever-increasing rate, driving the cosmos toward a strange and lonely future. The discovery of dark energy opened up a new frontier for cosmology, and a new generation of cosmic detectives has taken up the case. Their mission is to measure the history of cosmic expansion with unprecedented precision to figure out what dark energy truly is. Is it Einstein's cosmological constant, a steady, unchanging energy of the vacuum? Or is it something even more exotic, a dynamic field that changes over time, what some have called quintessence? To find out, astronomers are building bigger and better tools to survey the sky. One of the most powerful tools in this search is the Vera C. Rubin Observatory in Chile. When it begins its survey, this massive telescope will scan the entire southern sky every few nights, creating the deepest, widest movie of the universe ever made. It will discover thousands of new type Ia supernovae near and far, allowing us to map the expansion history with incredible detail. It will also track the subtle ways in which the images of distant galaxies are distorted by the gravity of intervening dark matter, a technique called weak gravitational lensing, which can reveal how the cosmic tug-of-war has played out over billions of years. From space, missions like the European Space Agency's Euclid Telescope and NASA's Nancy Grace Roman Space Telescope are designed specifically to tackle the dark energy mystery. The scientists behind these projects, Saul Perlmutter, Brian Schmidt, and Adam Rees, who shared the Nobel Prize in Physics in 2011 for their discovery, along with thousands of other researchers around the globe, are engaged in a monumental effort. It's a detective story playing out on a cosmic scale, using light from a time before our Earth even existed. Each new supernova discovered, each galaxy cataloged is another clue. The nature of dark energy will determine the ultimate fate of our universe. If dark energy is Einstein's cosmological constant, then the future is one of accelerating loneliness. The universe will expand faster and faster. Big freeze. Heat death. But what if dark energy is not constant? This hypothetical form is called phantom energy. The fabric of space-time would be torn asunder. There is a third possibility. Dark energy weakens. The cosmic expansion would slow, halt, then reverse, heading for a big crunch. We find ourselves at a remarkable moment in the history of human thought. We have pieced together a grand narrative of the cosmos, yet, at the peak of our understanding, we are confronted by our deepest ignorance. We have discovered that 95% of our universe is made of dark matter and dark energy, mysterious components we have only just begun to name. The quest to understand dark energy is more than just an academic exercise. It touches upon the most fundamental questions we can ask. Solving this mystery could lead to a new revolution in physics, one as profound as those ushered in by Newton and Einstein. It could change our understanding of everything, from the infinitesimally small realm of quantum particles to the infinitely large scale of the cosmos. This is the spirit of science. To stand at the shore of the cosmic ocean, to acknowledge its vastness, and to not be afraid of the unknown. The discovery of dark energy is a profound lesson in humility. It reminds us that we are still just beginning to explore the universe. We are children taking our first steps into a grand cosmic arena. So, the next time you look up at the night sky, think about this. Think about the silent, invisible energy that is pushing the galaxies apart. Think about the cosmic tug-of-war playing out over billions of light years. And think about the dedicated scientists, the cosmic detectives, who are working to unravel this profound mystery. You are living in the age when humanity first realized that our universe is being ripped apart, and we have embarked on the epic quest to find out why. The story is still being written, and the greatest discoveries are yet to come.